I'm Alyssa Goodman. I'm an astronomy professor here at Harvard, and I'm interested in how new stars form and how we can use computers in clever ways to learn about the universe and to teach people about the universe. So I work in basically three different areas. One is in astronomy, in star formation and the interstellar medium. Another one is in kind of e-science and the tools that people can develop to make science go faster and be more efficient. And then in science education, we try to use some of those tools to make learning science and studying science more interesting. So the first one, in the astronomy world, I got interested a long time ago in the physics of the gas between the stars, which we call the interstellar medium. And in particular, one reason that I think it's interesting is because over millions of years, under the influence of its own weight, so its self-gravity, it collapses and it forms eventually stars. And you can either say it that way in one sentence, or you can write thousands and thousands of pages about how this exactly happens and what magnetic fields have to do with it was one of the first things I worked on. And then how does the little bit of rotation that's in the gas as it collapses turn into constraints on how disks around stars that eventually form extrasolar planets form, and how does the structure of clouds in the sky give you ideas about the structure of these clouds of gas in interstellar space, and how do you combine techniques at different wavelengths to observe things like the density and the temperature and the velocity structure of these clouds. And so we've done observations of these clouds at all different wavelengths, from literally X-ray to long wavelength radio observations. But a lot of what we do these days is we work with people who make computer simulations of how the physics of the clouds, both on a galactic scale and on the scale where you form individual stars, how that works. And then we make what's called synthetic observations. So we take this fake world, a fake universe, and then we observe it with fake telescopes, and we make fake data showing you what you would observe if the simulation was right, with the same telescopes that we actually use, or mimics of those same telescopes. And then we do very fancy statistics to try to compare what you get from the simulation with what you get from the observation, because while pictures of nebulae and things that you've seen are gorgeous, they're also very, very complicated. And so to try to get really simple parameters out of that, the same way that you would, say, if you wanted to know the mass of a star. You know, a star is a sphere, you can kind of figure out the physics of how that sphere is held up. The same is not true for some complicated swirling cloud of gas. And so it's easier, rather than try to figure out the physical parameters like the density or something simple like that directly from the observations, you can play with those as inputs to the simulations and then try and find simulations that best match the observations to try and figure out what the physics of the region you're looking at probably is. So in the e-science world, one of the tools that I care the most about is data visualization and the manipulation of data in general in visual ways. So a long time ago, you know, I would just try to use other people's software in clever ways. And by clever, I often mean trying to include more context than people usually do. So sometimes that just means still, you know, statistical graphs, so XY graphs and bar charts and histograms and things, but being able to select, you know, particularly interesting regions in those graphs and see how those points show up in other graphs. And so that's called linked view visualization. And there are commercial tools that can do that. But when it comes to trying to include images or these volumetric descriptions of the gas, there are no commercial tools. And so about 9 years ago, we started a project called Astronomical Medicine, where we started using medical imaging software on astronomy data. And that was pretty successful. And ultimately, we published a paper, not ultimately, but about 5 years ago, we published a paper in Nature that was the first interactive, what's called 3D PDF. So we had this volume of space that you could click on in the article. You can still do this, and you can move it around, and you can look at it from other directions. And so that's the kind of thing that I like to do, you know, steal software from somebody else, some other field that has millions of dollars to develop it, and then find clever ways to share it in a more traditional format, which would be a journal, but still make it interactive. And so after that, we've gotten various funding from NASA and collaborations with Microsoft Research, where we work on something called Worldwide Telescope that lets you put all kinds of imagery and information in context, either on the sky or using manipulatable graphics. And so we have all kinds of projects like this thing called the ADS All Sky Survey that lets you see why the sky was studied over time. So visualization of heat maps on the sky showing you the density of particles. And then the biggest software project we have right now is called GLUE. So GLUE is an offshoot of this medical astronomy collaboration, where what you really want to be able to do, it's easier actually to explain in the medical context. So imagine that you have like a CT scan and an MRI and measurements of temperature, you know, in 3 dimensions taken from some other probe, okay, of somebody's liver area or something like that, okay? What you want is to be able to mold all that 3D information together so that it's registered in some way, which in astronomy you have coordinate systems that let you do that. In the medical world you have to do it a little bit more manually. But then you want to be able to see like, oh, is this place where, you know, the water concentration according to the MRI is high, also the place where the temperature is low according to this combination of CT scan, etc. And you want basically to be able to flexibly see and calculate things in all of the dimensions and all of the data sets that you have. And so what GLUE lets you do is basically link these data sets together so that you can ask those kind of questions. And so in astronomy you might have, you know, we might have a picture, for example, right now we're studying something called Nessie, which is a long, skinny, very, very long and skinny, like a ratio of length to width of like 800 to 1, okay? Cloud that's stretched out along the spiral arm of a galaxy. And we can see that on the sky at many different wavelengths, and then we can measure little points along it with different probes, and we want to be able to bring together all this information and link up, say, the coordinates for all of this information on the sky, but then we have lots of information that isn't about the sky, but it's about measurements of, say, the little dense blobs within there, and so we know their density or what their beta or what their temperature is. So we want to be able to do things like show me all the ones that are, you know, above 25 degrees and the estimate of the dust temperature, right? Does the spatial distribution of those, you know, have more importance in the optical map or the infrared map or the radio cube? And so you can just click and manipulate all of these images and data sets at the same time. So anyway, that's called GLUE, and it's being funded by the James Webb Space Telescope program through NASA, because the successor to Hubble, the James Webb Space Telescope, will have the ability to take these 3D data cubes through something called IFUs. So a lot of what we do is to leverage human pattern recognition and human cognition as the insight to then let you write statistical software that lets you not quite mimic the analysis that a person would do, but build on the analysis that a person would do. So the best example of that is, a lot of this is done in collaboration with Chris Beaumont, who writes the GLUE software and who did this project where there's these citizen science projects, like the Zooniverse runs a whole bunch of projects, and one of them is called the Milky Way Project. And that's to look at these beautiful images, I can show you some later, but images of the galaxy, the plane of the galaxy, that are taken in the mid-infrared, that show these kind of circles of emission. They're not really complete and they're not perfect circles, okay, but they're bubbles that are caused by stellar winds and H2 regions in the interstellar medium. And they're not perfect, but people can recognize them, and people can't quite describe what they're looking for, but you can kind of see this. Okay. So anyway, about 6,000 of these things were found in a citizen science project. And to give you some idea, when just graduate students were looking at the data, only 400 of them were found. So if you put a lot of people's eyes on it, you can find more things. But the problem is that that's not really very quantifiable in terms of how reliable these identifications are, what the properties of them are. So there's something called machine learning that we like to use, where you take examples of something that you want and you feed those examples to a computer, and then the computer can find you more of whatever that is without knowing, without actually understanding what you told it to look for. So anyway, we did that. We took the output of the Milky Way project and used it as the input to a machine learning algorithm, which then let us find all the bubbles in this data set and also quantify, how sure we were that certain things were bubbles or not bubbles. And it turns out if you try to do that a priori, with no human intervention, no human guidance in the first place, it's somewhere between extremely difficult and impossible. But obviously you also don't want to rely on people to find every single thing in a gigantic data set. So I really think that the way of the future is to teach computers to be almost as smart as humans and then let them run with it. finding ways to exploit the full dimensionality of the data. So in these cases where you can take spectra at a large number of positions, you really do have information about the intensity of something, emission from some gas, in 3 dimensions. Okay, and people were mostly plotting that in 2 dimensions. And so any way that you can get to really see what's going on in 3 dimensions is fantastic. Okay, and so you know, I remember seeing. We did this survey called the Complete Survey of Star-Forming Regions that uses like 8 or 9 different techniques to observe 3 very large regions that form stars on the sky. And the student who worked on the astronomical medicine project, Michelle Borkin, she was instrumental in putting those data in these 3D medical viewers, and suddenly we could see things like that there were weird loopy connections in 3-dimensional space between big blobs of gas that previously people had thought were 2 separate things along the line of sight, but you could see these connections. And so being able to see things that you can't see any other way is really what I like. And so there was that, the sort of whole astronomical medicine, and let's do this in 3D. And then the other thing is this recent discovery of this Nessie cloud, where people knew that there was this long skinny cloud, but we actually figured out that it was way longer than we originally thought, and that it seems to tell us something about the structure of the galaxy. And you can really only see that very clearly by looking at many different data sets from many different points of view. And it was really software like GLUE and Worldwide Telescope that let us make those additional views. How did I start my career? Okay, so I was going to be an oceanographer once upon a time when I was little. I wrote to Scripps Institute in California to ask what I had to do from the age of 8 years old till I would be a professional Jacques Cousteau, if you know who Jacques Cousteau is. And then somewhere along the way I decided I'd be a doctor, but then I decided that was a bad idea when I realized I couldn't handle death. By the time I was in graduate school, I guess I was pretty committed to astrophysics. I liked it a lot, and I just thought, all right, see what happens. And I got a postdoc at Berkeley, and then I was very lucky to get this job at Harvard, and I don't know, I like this job a lot, so I don't plan to change anytime soon. Oh, I think just plain old curiosity. I think like, wow, this is cool, I wonder how that happened. And then, you know, so on the astronomy side, it's just, you know, I want to know, like, and I know these unusual techniques that some astronomers also know, but I think astronomy is a small enough field that every astronomer has some weird combination of techniques that they know that other people don't know, and so you want to, I mean, sometimes obviously you have to learn more of them, but you know, you want to sort of bring that to bear on whatever problem you think you can solve that looks interesting, and so it's pretty much like being a little kid, and you know, wow, that looks cool, I wonder how that happened, except that instead of just being able to poke at it, you know, we can turn Hubble toward it. And then in the technology world, it's that I get incredibly frustrated with the tools that we use sometimes, and if I think I know ways to make them better, I just try to make them better and to work with a lot of people who help make them better. I don't do much of this myself. And then on the education side, I watch how science gets taught in schools now, and it's dreadfully dull, and it seems like a recipe and like a complete, you know, step-by-step process, which scientists know it completely isn't. And so anything we can do to make it not seem that way is what we try to do. That's a good question. What makes us a successful scientist? So I think it's some combination of curiosity, I think, is number one. I think raw intelligence is very important, but I think that people think that if you're just smarter, you'll be a better scientist, and that's not true. You have to be smart enough, okay? And once you're smart enough, then it's really curiosity and the ability to talk to people. And you know, a lot of kids who are interested in science when they're little don't really love talking to people. And so I think that people really undervalue the ability to communicate, especially even face-to-face, or to meet with people, or to do things together with people. And so I think that kind of collaborative spirit is probably the most underrated in the way that science is taught. And then I think curiosity is as important, if not more important, than raw intelligence. This is going to sound like a strange answer, but running out of money. Uh, so essentially technology becomes more and more and more expensive, and you used to be able to do a lot of science and astronomy for a lot of money, but not insane amounts of money. And now some technology, like cell phones that are used widely, get cheaper and cheaper. But the absolute bleeding edge of technology, like the James Webb Space Telescope or ALMA or the Square Kilometre Array, just get more and more and more expensive. And so they cost many billions of dollars. And so it means that the amount of data and information that any one astronomer can get out of that is pretty small. And so I worry that there isn't enough money to kind of cover the landscape with all of the technologies we could use to do science. And so one interesting way to think about that is, well, maybe if you spend a little bit more on making the data more discoverable and more distributed and more reusable, then you can use technology to save yourself from the cost of technology, because you can learn a lot from data that has been taken for another purpose, or that has been taken to, say, survey the entire sky, and whatever it is you want to look at, it's already been observed. Usually not at the absolute maximum resolution and sensitivity, but the world is going in that direction, so that the whole sky is just surveyed at every wavelength at the maximum resolution and sensitivity we know how to survey it every night. So now we're not there yet, but we're a heck of a lot closer to there than people 20 or 30 years ago thought we would have been. I remember being at a party in Washington, D.C., where some friends of my in-laws asked me, why the government should spend money on astronomy, because it's so useless. And, could I give them some examples of technology spin-offs from astronomy? And of course I could. But usually there's a time lag of 10 or 20 or even 100 years. All the GPS satellites, right? If we didn't understand orbital dynamics, there would be no GPS, You can give people really simple examples like that, but, when did we figure out orbital dynamics? Centuries ago, right? This is not something that happened overnight. On the other hand, some of what we do is actually immediately applicable. So, for example, the GLUE visualization software will actually be directly useful in medical imaging. Okay, so we can steal from the doctors and then give back. And so that makes it very attractive to me. And also a lot of what we do to make software like Worldwide Telescope or other kind of online research tools better for research also make them better in education. So there's a way to transfer what we do as research tools to becoming education tools. So, mostly my answer is science is fine for the sake of science, pure discovery and creativity, the same way you'd fund art, okay? Except, 100 years down the road, it's probably more useful than art, as much as I like art, okay? But if people always want to see some immediate return in a form of technology, for example, from astronomy or physics, they're going to be disappointed. They have to shift their definition of immediate to be tens of years. I don't know. I mean, in the short run, yes. Civilizations have come back from the dead, essentially. And it's only a question of whether we do things to destroy our planet in ways that are not recoverable by us. So, there's a really good chance that climate change will change the planet in ways that we as humans cannot fix, and that it'll just completely reshape society. Do I think we'll wind up in a Mad Max scenario? No, but do I think that there'll be like an absolutely different way of life for 100 years while people figure that out? Unfortunately, yeah, I do. Unless somebody does something really soon to sort of start a global campaign to mitigate climate change. And I know that a lot of people are talking about that, but I think in a lot of countries the politics is just too short-term thinking to let that happen. So I'm hoping this changes. In the world of star formation, there's going to be an interesting meeting of the minds and of the research between the people who study star formation in very far away galaxies and the people who study star formation in our galaxy. And it's going to be not unlike about 20 years ago, people were talking about wow, you know, star formation should really be relevant to planet formation, if there is any such thing as planet formation. Because if you think about it, it was just under 20 years ago that people started finding planets outside of our solar system. And so really, if a star formation person was asked to go to a meeting, as I was, with some planetary scientists, it was like, well, how did the solar system form? How interesting a question is that? There's only one of them, you know. But, you know, really visionary people were thinking, of course there's more than one of them, you know, and we should really start figuring out how, when you form a star, you know, what happens to that stuff around the star and how does it form planets. And we didn't have the resolution in studying star formation, fine details, to see anything that would be relevant to planet formation, again, until about 20 years ago. And then it started to be possible to see those details, and suddenly this intersection of those fields got interesting. And so I think the same thing is happening now, where in faraway galaxies we can hardly see individual regions that are forming stars, and certainly not individual stars forming. But we're getting closer and closer. And then here in our galaxy, we're starting to understand these processes a little bit better. And, you know, could we apply what we know? So we're kind of like the planetary scientists in that world. You know, we're the small-scale people. And can we talk to the large-scale people and tell them things that are useful and, you know, bridge that gap? So I think that'll happen. It's starting to happen a little bit. I think it'll happen more. And in the technology and visualization world, I think that visualization and clever tools to look at large data sets and large interconnected data sets will become not something that's just a luxury to those of us who like to do that kind of thing, but an absolute necessity. And it's kind of the way that a lot of people resisted, you know, writing with computers, and they still wrote things longhand, and nobody does that anymore. Okay, so technology, you know, completely changed the way people write and communicate, and I really think that just taking data without having clever ways to look at it and analyze it that involve some form of visualization and statistics is just not going to be a plausible way to do science. Well, I think that any country where the students can take their education into their own hands a little bit more will have a big advantage. There's a lot of online learning platforms, there's a lot of clubs, there's a lot of ways to get around this, and then of course sometimes there are opportunities to actually try to change the curriculum in schools. But in science in particular, as I mentioned earlier, I think that it's taught as a series of somewhat connected facts and as kind of a cookbook. You know, here's the scientific method, and we have a hypothesis, and then we do this, and then we do that. And that is just nonsense. You know, people kind of know something about some process or something, and they go, well, that's interesting. I wonder if it also does this. You know, I wonder if I could test this way, it might work. And then they poke around and they try it, and then they, you know, test whether or not another hypothesis is better. But it's not like somebody knows in advance step A, B, C, D, like in school. And so I think if Bulgarian students can find a way to explore science in a more realistic, curiosity-driven way, which doesn't mean that you don't have to know the basics, that they would be at a competitive